this problem, we have a 5.4 kilogram bag of groceries, and it's stationary on an incline with an angle of 15 degrees. We want to find the normal force of the incline on the bag. So the reason that the bag of groceries is not sliding down the ramp is because friction is preventing it from sliding. Since it is stationary, we know that this is static friction. The first thing we want to do, as always, is draw a free body diagram. Here's my bag of groceries right here. And my first force I always draw in is the gravitational force, which is always straight down. And I'll label that as Fg. Second, we have the normal force. There's a surface, so there's always a normal force. And the normal force is going to be at a slight angle because of the incline. It's perpendicular to the surface. So it's not straight up, but it's angled at a slight 15 degrees. Being there's a surface, there's also a friction. The friction prevents it from moving. So it wants to move down the incline. That means that the friction is pushing up the incline to prevent it from moving down. And it is parallel to the surface. Because it is stationary, we know that it is a static friction, not a kinetic friction. The first thing I'm going to do here with this free body diagram is I'm actually going to rotate some things. And the reason is because it's going to make things easier later on. If I draw the forces on here itself, currently I would have, if I look at my Cartesian coordinates, I have two forces that I'd have to break into components. To make things easier, what I'm going to do is I'm actually going to rotate this. I'm going to rotate it so that the normal force is upward and the static friction is to the right. And in this situation then, we have it that it's actually the gravitational force that is going to have to be broken into its x and y components. So the trick to this is to make it so that we only have to break one force into its x and y, not two of them. So it's going to make it easier for us later on. So I'm going to now rotate this free body diagram so it looks like this instead. I'm going to rotate this back to the way it used to be because I actually want to find what this angle is right here. In order to do that here, I'm going to have, this is a triangle here. This is a 90-degree angle and this is 15. So that means that this angle here is actually going to be whatever's left over. We have 180 degrees for a triangle. We have 15 plus 90 plus whatever this is. And so we can figure that out easy enough, and that comes out to be 75 degrees. Now if I move this down, right here, these values here, move this down, it doesn't really affect any of the angles as I do so, but what I can see is I can see that this here plus, and I have to move this dotted line as well, I'll just redraw the dotted line, plus this here makes a 90-degree angle. All this together is 90 degrees. So if this is 75, that means that this angle here, which corresponds to my free body diagram right here, is also going to be 15 degrees. So it turns out whatever the angle of inclination is going to be the same as the top angle on the gravitational force of your free body diagram. So that is also a 15-degree angle. And we're going to break this into its x and its y coordinates. But before we do that, we have to write down what our givens are. We have a 5.4 kilogram grocery bag, so that means that the mass is 5.4 kilograms. It's really all that we're given, but we always know that the gravitational field strength is 9.81 newtons per kilogram. So we're going to use that later on as well. We want to find the normal force. So we're looking for F sub n. We're looking for this force up here in our free body diagram. Now the first step that you want to do when you approach this problem is we are going to solve for that gravitational force. The mass is of no help to us. So whenever you're given the mass, your first step is to solve for the gravitational force using the gravitational force is mass times 9.81. Mass was 5.4. Gravitational field strength is always 9.81. And we get that the gravitational force is 53 newtons. Now that we know the gravitational force, what we're going to do is go back here, and we're going to look at this triangle here, this bottom triangle, and break this gravitational force into its x and y components. So first step always is to solve for the gravitational force. In any kind of force problem, if you're given the mass, solve for the gravitational force first. I'm going to redraw this gravitational force triangle. I have my y and my x components. This here I now know is 53. And remember, this top angle is always the same as the angle of inclination. The first thing I'm going to do is solve for the x component. I'm going to have to use my SOHCAHTOA. I'll label my sides. This here is the hypotenuse. My angle's at the top. The opposite of top is the bottom, so the opposite. And the one left over is the adjacent. We'll solve for the x component first. The x component is the opposite. And we know the hypotenuse, so we're going to use the sine. Sine of 15 is equal to the opposite, which is my f sub x, over my hypotenuse, which is 53. Remember that the sine of 15 really just represents a number. You can either look it up on your trig table or type it in your calculator. And that is 0.259, which equals fx over 53. I multiply each side by 53, and I get my x component to be 13.7 newtons. Now we're going to get the y component. And to get the y component, that's the adjacent side. We know the hypotenuse is 53. So we're going to use a cosine. Cosine of 15 is the adjacent, which is f sub y, over the hypotenuse, which is 53. Remember that the cosine of 15 simply represents a number. You either look it up or type it into your calculator. It is 0.966. That's f sub y over 53. Multiply each side by 53, and you get that the y component is 51.2 newtons. Now again, I'm going to redraw this free body diagram. I'm essentially replacing that hypotenuse with its two components. So now as I redraw this free body diagram, I have my normal force, which was up. I have my static friction, which was to the right. And then I have my two components, my y and my x component. Now because it is stationary, we are in equilibrium, which means all the forces balance each other out. That means the force on the left, which is the gravitational force, the x component, of the gravitational force. So the force on the left, f sub x, equals a force on the right, which is f sub s. We just solve for f sub x. 13.7. So I can now replace f sub x with 13.7. So since this is 13.7, this must also be 13.7. They're in equilibrium, which means that they are equal. I'm going to do the same thing with the y component, the y direction. F sub n is up, f sub y is down. And they balance each other. That means f sub n equals f sub y. We just solve for f sub n, or I'm sorry, we just solve for f sub y, I should say, which is 51.2 newtons. So now I can replace f sub y with 51.2 newtons. That is also my normal force. Now if I go back here, my main objective was to solve what is f sub n. So out of the two values, this is the one that is my answer. The normal force is 51.2 newtons.